you very much for the introduction. Hello everybody. First of all, I would like to thank the organizers for the invitation and this great opportunity to present my research interest and the main result of my PhD with Matthias Christhandl at ETH Zürich. First, I would like to give you an overview of my presentation. At the beginning, I will motivate my talk, so it's essentially based on Pauli's principle. And in the second part, we will relate this motivation to the quantum marginal problem. And we will learn that if we consider n-fermion quantum states, that the anti-symmetry on the particle exchange will lead to further restrictions on occupation numbers. And then to use this mathematical structure for physics, we will study a concrete physical model, we will solve this model, and we'll investigate this model from this new viewpoint. Later we will find an interesting physical behavior, the so-called quasi-pinning effect. And at the very end I will explain why this nice property and this nice physical effect in the one-particle picture has a physical meaning. This means I will explain how to reconstruct the structure of the corresponding n-fermion state. So in 1925, by studying electronic transitions in atoms, Pauli has formulated his famous exclusion principle, which states that no two identical fermions can occupy the same quantum state at the same time. Mathematically, or a slightly more modern version, you can formulate it like this. The particle expectation value for a quantum state that I described here by I is not only bounded by 0, but also by 1. These constraints here, they're relevant whenever, for a concrete physical system, we observe occupation numbers very close to the minimum or maximum. So, ni close to 0 or close to 1. I would like to introduce some notation which explains this. Whenever we observe an occupation number ni exactly equal to 0 or close to 0, I would like to say that the occupation number is pinned by this constraint to the minimum 0. It cannot be more negative, cannot be smaller. And in the same way, if an occupation number is exactly 1 or approximately 1, I would like to say that the occupation number is pinned by this inequality to the maximum 1 or quasi-pinned. This Pauli exclusion principle is very important for the understanding of physics and chemistry. So one prime example is the very famous Aufbau principle, which explains the main structure of atoms. So we study the atom, okay, they have some energy shells. Let's think about zero interaction between the electrons. So with these 1s shell, 2s, and so on. And to get the ground state, we just fill these energy shells according to Pauli's exclusion principle. And then at the end, the main properties of the atom are just given by the sum of all the properties of all occupied energy shells here. And although this exclusion principle is so important, it was already strengthened 1 year later by Dirac and Heisenberg. They identified the exclusion principle as a consequence of a much deeper mathematical statement, namely the anti-symmetry of the n-fermion wave function and the particle exchange. So one can easily see that this anti-symmetry will imply the exclusion principle, but the converse does not hold. Yeah?
Did they have this idea independently, or Dirac and Heisenberg?
Can you say it again, sorry?
Did they have both this idea independently? Did they come up with this independently?
So I'm not sure whether they talk to each other, but there are many people actually, also Wigner, who contributed to this. But I think there were quite many people who had this idea. It's just the indistinguishable character of these electrons, and then you can of course derive this. I think there were many people, probably not only these two, who had this idea. So since this anti-symmetry is stronger than the exclusion principle, there's a natural question arising here, whether there are further restrictions on occupation numbers. Restrictions which are strengthening the Pauli exclusion principle. And naively, if such constraints exist, we expect that they play a role for physics whenever they are saturated, when they are pinned. So to give you an overview of the mathematical objects, which are quite simple, that I will use here, I'd like to present this here. So we talk about n-fermion quantum systems, and n should be a small number, so think about atoms, okay? And the particle number is fixed. So we describe these physical systems by quantum states, psi m. So they are anti-symmetric on the particle exchange. Mathematically, this means that there's given a one-particle Hilbert space, H1, and the state is lying in this n-fold anti-symmetric tensor product. Okay. And it's more natural to talk about density operator, so here I would like to talk about rank 1 operators. And whenever a physicist asks about some one-particle properties like the occupation numbers or the electron density, this state rho n contains too much information. The appropriate object is the so-called one-particle reduced density operator, rho 1. So obtained by applying a partial trace and tracing out n minus 1 electrons from this state here. And notice that we choose a slightly different normalization of rho 1 here. We normalize rho 1, we trace normalize it to the particle number n. This has the advantage that the eigenvalues of rho 1 can be interpreted as occupation numbers, the so-called natural occupation numbers. The occupation numbers with respect to the eigenvectors of rho 1. And here, for this research area here, since the mathematics behind it is so complicated, we always restrict to finite dimensional Hilbert spaces. So here you can think about rho 1 as a Hermitian matrix, and these natural occupation numbers as a finite vector. We collect them as a lambda vector.
What is the phrase natural occupation number mean?
Well, the word occupation.
I mean, you have one particle state, and you ask how many electrons are sitting in this one particle state, this occupation number. And natural means that they have the occupation numbers with respect to a very specific basis, one particle basis, the eigenbasis of rho 1. And actually, these natural occupation numbers, they play the central role for my presentation, my research. So in the following, I will talk quite often about lambda vector, this natural object. So the question that I addressed before, so this anti-symmetry which is stronger than Pauli's exclusion principle, this question that I addressed can be formulated as the goal to translate the anti-symmetry from the n-particle picture downwards to the one-particle picture, to find further restrictions on occupation numbers. This is the general question at the moment. So I would like to show the connection to the quantum margin problem. So we learned from the previous slide that every anti-symmetric state psi m, for every anti-symmetric state psi m, we can calculate the corresponding one-particle reduced density operator. So I can do it for the set of all anti-symmetric states. So I get the set of all corresponding one-particle reduced density operators. And then a goal might be to describe this set here. Which rho 1s are possible? Is every rho 1 mathematically possible? I would like to answer this question now. Actually, this question is called Fermionic quantum margin problem. So reduced density operators are also called quantum margins. And as a first step towards the solution of this question, notice that there's a unitary equivalence. So assume, consider a rho 1 which belongs to the set here. This means that there exists a psi n here, such that psi n leads to this rho 1. Now, let's take an arbitrary unitary operator on the one-particle Hilbert space, call it u, and multiply u from the left and right hand side to rho 1, so here is a decker. So since u is unitary, this is again a density operator. And moreover, it turns out that this density operator also belongs to the set, because you can find the corresponding state here. It's just the original state multiplied with n copies of u. So this is again a antisymmetric state. This means that to describe the set rho 1, we just need the spectral information. Just the lambda vector is relevant to describe this here. And the original question of the antisymmetry from the viewpoint of occupation numbers is exactly equivalent to solve this problem here, to determine all those rho 1s.
That arrow should go both ways, right? The arrow below.
Exactly, yeah, of course, yeah.
Two ways.
Yeah. You can just plug in the identity. So, how does the solution of this question look like? So, symbolically, drawn here, all antisymmetric states, so the Fermionic and particle Hilbert space. For every psi m, you can calculate the corresponding lambda vector. So it's lying somewhere in this high-dimensional Euclidean space, so it's just a simplified two-dimensional picture here. So I have drawn quite many lambda vectors here. And clearly not every lambda vector is possible. We already learned as Pauli's exclusion principle, which restricts lambda vector every lambda vector to this Pauli hypercube here. So this hypercube corresponds to the Pauli exclusion principle, which can be here formulated as every eigenvalue lambda I should be between 0 and 1. But surprisingly, it turns out not every lambda vector inside of this hypercube is mathematically possible. The set of all antisymmetric states maps to a proper subset, to a polytope, which I call P and D. It depends on the particle number n and the dimension d of the one particle Hilbert space. This polytope for arbitrary n and d was found by Alexander Klyashko just a few years ago. So he provides an algorithm for fixed n and d for calculating this polytope here. And notice again that if a lambda vector lies here, it fulfills Pauli's exclusion principle, but it's mathematically impossible. So this is just about the mathematics, it's not yet related to a Hamiltonian or whatever. So, of course, you all know how to describe polytopes. So given a high-dimensional polytope in a simplified picture, there's Cartesian coordinates. So for every polytope, we can take one facet, extend it to the hypersurface, and consider all points below it. And do it the same for this facet, consider all points on the right side. So clearly, a polytope, as you know, is the intersection of finitely many half spaces. You all know from your school time how we describe half spaces. So the hypersurface here is then described by equality, and here's a linear form which explains that it's flat here. And the half space below is then just given by the same object here, but with a smaller equal sign or larger equal sign. So the point that I want to make is that the solution of this fermionic quantum margin problem is given by a finite family of such inequalities which are linear in these Cartesian coordinates in the natural occupation numbers. And we call those constraints generalized Pauli constraints. To give you an example how non-trivial this is, let's consider three fermions. So you can think about a lithium atom and a six-dimensional one-particle Hilbert space. First of all, we would like to order these natural occupation numbers decreasingly. Makes it simpler at the end to describe the polytope. So lambda 1 larger equal lambda 2 and so on, lambda 6 non-negative. Moreover, we have the normalization. The sum of all 6 lambdas is equal to the particle number, so n equals 3. And now the non-trivial constraints. So far it was just boring constraints. I can show that the sum of the two largest occupation numbers, lambda 1 and lambda 2, plus the fourth largest, is smaller or equal than 2. So notice that this constraint is manifest stronger than Pauli's exclusion principle, which just states that lambda 1 plus lambda 2 should be smaller or equal than 2. Moreover, there are three further constraints, non-trivial constraints. The largest occupation number plus the smallest one should be smaller or equal than 1. This is again stronger than Pauli's exclusion principle. Lambda 2 plus lambda 5 smaller or equal 1, and the two guys in the middle also smaller or equal than 1. For this small setting with n equals 3 and d equals 6, something very specific happens. You can just add up these three constraints here, and you get on the left-handed side, due to this 3, on the right-handed side also 3. So we can see that artificially we get 3 equalities here. For all larger settings with larger d and larger n, we just get inequalities.
What about n equals 2?
Actually, for n equals 2, there are no inequalities, but there are some very strong restrictions, namely every non-zero natural occupation number should be evenly many times degenerate.
Be what?
Evenly many times degenerate.
What does that mean, degenerate?
So you can say lambda, let's say I is an odd number, lambda I is equal to lambda I plus 1. This follows from the antisymmetry and Schmidt decomposition.
They just come in pairs, you're saying?
Yeah, exactly.
Oh, okay.
And it can also happen that 4 are identical, but always at least 2 and then 4 or 6, whatever. So all non-zero. This is actually the strongest restrictions, but for this research it's boring because there are no inequalities that we can check, so as you'll see later. So this is also a reason why I will focus on 3 fermion systems, 4, 5 and so on, and not on 2.
I mean, I'm familiar with the mathematics, but not with the physics and the chemistry. So is there kind of just a physical statement you can make based on these eigenvalues about, something new that people did not know about these atoms or molecules?
Yeah, this will be my research and my results that I will present to you
That's
today.
great. Good. Sorry.
In this particular case, and it's easier to see in this case than the other ones, if you look at these conditions, these pairings, what it means that if you had 6 particles and you looked at all the possible Slater determinants, you would get 6, 2, 3, or 20 Slater determinants. These conditions can only be satisfied with 8 Slater determinants. So you really reduce the variational problem from 20 Slater determinants to 8 Slater determinants with a canonical form.
So this is not very good that you mentioned this because now it reduced my result at the end, the quality of my result. Thank you very much.
In the other cases, it doesn't reduce to something that...
Yeah, that's true. Yeah. So you can see these results. Actually, they were not found by Alexander Glashko, or they were found first by Boland and Dennis and Mary Bersowski. But Glashko found the algorithm for arbitrary n and d. And to give you an impression, and since this setting is so important for the presentation, I built the corresponding polytope here. These equalities here are actually very important because you see we have 6 natural occupation numbers. So we talk about the 5-dimensional polytope due to normalization, 5 dimensions. But due to the 3 equalities, it reduces to a 3-dimensional polytope. That's a good point. And we can build 3-dimensional polytopes. And I take the following lambda 4, 5, and 6 as the independent variables. And this is the polytope, okay? It has 4 facets. 3 facets are actually quite boring because they correspond to saturation of these inequalities. But one of the facets, this one here, with the word pinning written on it, corresponds to saturation of this inequality, so of the only inequality which is non-trivial here. So it also explains here lambda 4 equal lambda 5 plus lambda 6. So I would like to hand it out to you. You can have a look at it. So it will play an important role, and while you're touching it, you will see how concrete these constraints are.
What's the largest permitted value of lambda 4? I could probably read by studying your polytope.
So it's 1/2.
1/2. Okay.
Can I make another comment? First of all, I didn't find these conditions independently. I just gave a different... Borland and Dennis were the ones who found these conditions. And notice the date is 1972. They also had some conjectures for n equal 3, d equal to 7.
Exactly,
but
yeah.
were unable to prove them. And Klyashko's work was, when it was announced in 2005, it was literally the first progress in this question for over 30 years. So from that to Klyashko's results, there was a 30-year gap in which absolutely nothing new was learned. That gives you an idea of his achievement. Sorry, okay.
Thank you very much. It's an important comment. So it's a fantastic work by Alexander Klyashko, and it's quite disappointing that he can't be here. So I'm very grateful to him.
But actually, so if you allow for mixed states, then this condition disappears, no?
Exactly, unfortunately, yes. So
what does that mean in practice? It means that if you would do...
So we have to...
you would not... Well...
We should restrict... If you can restrict to pure states on the total level, then you're fine and you have these constraints. But of course, if you couple your physical system to a second system and get some mixing, some mixed state, then they are softened. I mean, if you just allow arbitrary mixed state, then of course, there's just Pauli's exclusion principle. But if you have a statement on the eigenvalues of the n-part density operator that one occupation number is close to 1, and all the others should be 0, then you get approximatively such a structure.
Exactly, that's my question. So what happens if somehow there's some notion...
Yeah, they're just becoming weaker, but it's not... It's still more...
Write them down exactly.
Exactly, but it's more complicated. I cannot write it down now.
They are still linear.
Exactly. But it's more complicated to write them down now. Alexander Klyashko also did this. Okay, so now we have this fantastic, beautiful mathematical structure. And see, Alexander Klyashko did a great work, great job, and whenever a mathematician is doing such a great job, there's high potential to get good physical results with that, because he found the structure and now we should apply it. But it's not so easy to use it for physics, because it's a very new concept. And first step towards the application to physics is first to check how does nature look like from this new viewpoint. So there's given this polytope now, and this polytope just depends on the particle number and dimension of the one particle Hilbert space, so not on the Hamiltonian. So let's take a concrete physical system and a distinguished state like the ground state of first excitation and check the position inside of the polytope. Are we in the middle or are we on the boundary? If we are on the boundary, we say we are pinned on the boundary, we're pinned to the boundary. I would like to explain to you why pinning might be so interesting. If a physical state is prepared on such that the occupation numbers are lying on the boundary, this polytope describes a kinematical constraint for the system in the following sense. If you switch on a time evolution, so a unitary time evolution, this is important here, then you can say one thing for sure, I mean that the point cannot leave the polytope under the time evolution. And you can imagine for some time evolutions the point would like to leave the polytope, but this is then not possible anymore. And exactly in those cases, the time evolution is then more determined by the geometry of the polytope and not by the Hamiltonian anymore. And this is actually a generalization of this here, what you know quite well. Let's come back to the atom, and let's couple this electronic system to photons. This means this electron in principle might decay to a lower state. So it's, from an energetic viewpoint, it's meaningful to do this. But Pauli's exclusion principle does not allow this. And this is a generalization of this picture. And also in solid state physics, if you have a solid body at low temperatures, the physics is determined by the electrons around the Fermi level. There's a large class of states or physical systems which are very, very boring, but as a first step, it's interesting, it's worth to consider them. You consider, let's say, n non-interacting fermions. So the n particle Hamiltonian is given by a sum of n1 particle Hamiltonians, and just think about kinetic energy plus the confinement potential. To understand the physics, we should solve the corresponding n-fermion time-independent Schrödinger equation, which, due to the simplified structure of the Hamiltonian, can be mapped to a one-particle Schrödinger equation. Just one particle Hamiltonian, and we are solving the one-particle eigenvalue problem. Let's say we succeed with that problem, and we find the solution of one particle energy state and corresponding one particle energies epsilon I. Then we can easily reconstruct the information on the important n-particle picture. For example, the ground state is just given by a Slater determinant of the n lowest one particle states. So this is my symbol of a Slater determinant. So the anti-symmetrized tensor product of those n one particle states 1 up to n. And clearly for this Slater determinant, it's very easy to calculate rho 1, just the projection operator onto the n lowest one particle states. The natural occupation numbers, even more obvious, just n times 1, and then some zeros. This state is very boring, but it fulfills actually, it saturates Pauli's exclusion principle. So you see we have either ones or zeros here. So we have pinning here of this constraint and of that constraint. And in my simplified polytope picture, this two-dimensional cartoon here, this spectrum here corresponds to this point here. You see some natural occupation numbers are 0 and some are 1. And of course this is the point of the polytope because you know psi n exists for this state. And it's important to notice that in this picture here, this is not only just one Slater determinant, but it's just the family of all single Slater determinants. So independent of what 1, 2, and n is, you get always this point here. So now we would like to switch on an interaction between the fermions. It's not so easy to get some analytical results then for arbitrary models. So what are the requirements for a non-trivial model? We would like to consider fermions which are coupled to each other with a coupling strength, let's say delta. We would like to be able to at least calculate the ground state of that model, psi n. Moreover, we would like to be able to trace out n-1 fermions, which is non-trivial again because we have to calculate n-1 integrals. And in a third non-trivial step, we would like to diagonalize this density operator. So you see, we have 3 non-trivial steps, and typically already the first one is impossible. And after all, it should be analytically in delta, so a function of delta. Fortunately, there's one model that one very simple model for which it's possible. And I think this is probably the only continuous model for which you can succeed with all those 3 steps. This model here, described by this Hamiltonian, so we have n electrons, n particles, n identical particles, for simplicity in 1 dimension, without spin, with kinetic energy and a harmonic confinement trap, okay, with a shape m omega squared, and we couple all those n particles harmonically to each other with a coupling strength d. So first I would like to consider this Hamiltonian on the n particle Hilbert space, so without any symmetry constraints. So we just talk about the square integrable functions over R to the n. So this is our n-particle Hilbert space. The Hamiltonian can then be written as kinetic energy plus a potential. And I can choose this matrix M symmetric. I think most of you have solved this eigenvalue problem as undergraduate students. So we can just diagonalize the symmetric matrix and then get the eigenstates and eigenenergies of H. There are actually two natural length scales arising here. So by diagonalizing M, we decouple these harmonic oscillators. We get one harmonic oscillator for the center of mass motion with a natural length scale L. Then we get n minus 1 harmonic oscillators describing the relative excitation between the particles. The natural length scale is called L tilde. You see, if the interaction D is set to be 0, this term here vanishes, and L and L tilde are identical. So the only important thing from here, what you should remember, is that for zero interaction, L and L tilde are identical. And for weak interaction, they're very close to each other. This is the important message for the future. Of course, to study these generalized Pauli constraints, we should restrict ourselves to the fermionic subspace. So we would like to find the ground state within the Hilbert space of antisymmetric n-particle states. This ground state can easily be calculated. So I did it actually in 2011, and there's also a paper in the archive at the same time. So the state is given here. So it consists of two main parts: a polynomial. It's actually the Vandermonde determinant. It's antisymmetric on the particle exchange. So clearly, the second part, this exponential function, should be symmetric on the particle exchange. And yes, that's the case. As you can see, here we have x1 up to xn, the sum squared, and then x vector squared, so the collection of all coordinates. And notice that for zero interaction, since both length scales are identical, this term vanishes for zero interaction. In that case, the exponential function decouples in the coordinates x1 up to xn, and since this is the Vandermonde determinant, psi n has indeed the structure of a single slated determinant. So this is kind of consistency check. Moreover, it's quite funny, you can also consider this model as a model of n-identical bosons. And then it turns out that you find exactly the same ground state, but without the polynomial in front of it. So the differences between fermions and bosons are just hidden in this Vandermonde determinant. Moreover, the state has some similarities to the Laughlin wave function. It's also very interesting. So then one can trace out n-1 fermions. It's elementary, but not that easy. You get this structure here, exponential function with the quadratic form, and a polynomial which corresponds to this Vandermonde determinant. So again, the differences between the fermions and bosons are just hidden in this polynomial P here. Then with a lot of effort, one can also get the natural occupation numbers, at least numerically, or with some perturbation theoretical approach.
So
I guess you don't feel like showing.
want to make sure what is the n? Okay, is just the function.
Sorry?
What is the n? What is the n? Is the
This here?
yeah.
Just normalization.
Oh, okay.
I imagine you don't feel like showing us alpha and beta. They're probably
Actually, I skipped them half a year ago in my talks, and so I can show it to you if you like. But actually, they're not so difficult to be calculated, but I can show it to you later if you want. I think they're more complicated, but not very spectacular.
Mm-hmm.
Actually, what's quite interesting to see, I mean, for zero interaction, beta vanishes. And you can also say, you cannot analytically diagonalize this operator here anymore, or this kernel. So yeah, I resort to numerical tools or perturbative tools. And the reason for this is actually two viewpoints how you can see it. One is, you can say, due to this polynomial in front of it, you cannot diagonalize it anymore. Without this polynomial, it's just the Euclidean Feynman propagator for the harmonic oscillator, then you can diagonalize it. Or for zero interaction, beta vanishes, and then you can also diagonalize this more or less by using Hermite functions. So let's say lambda vector is given now. Okay. First, I would like to show you some properties of lambda vector. Due to the structure of the Hamiltonian, it's clear that the lambda vector just depends on the ratio of the interaction strength d and the external potential strength m omega squared. One can easily see that it means it depends just on the ratio of both length scales. From now on, I would like to restrict to n equals 3. I found a surprising duality. So if you just swap the two length scales, you find the same natural occupation numbers. This duality somehow connects the attractive and repulsive interaction regime. So if you just swap them, you change the sign of D more or less.
Does this depend on the restriction n equals 3?
No.
Okay.
I found it for 4, 5, 6, and 7. And these are the only settings that I succeeded to discuss, but I think it holds for all n.
Okay.
But the funny point is, I cannot prove this on the n particle level so far. So it seems to be a kind of hidden symmetry which shows up in the one particle picture. It's very interesting. And the important point for me was that due to this duality, I can introduce a very smart interaction strength delta. I just introduce e to minus delta as the ratio of these. By doing this, you find that lambda vector's function of delta is symmetric. And since I also confirmed my numerical results by perturbation theory, so I just took the one particle reduced density operator as function of the interaction strength, it's very important to have this duality because this means in the Taylor expansion, or in the expansion, all odd orders are vanishing. And for you, it's important to remember that the weak interaction regime that I will consider the following, that this regime corresponds to delta smaller than 1, much smaller than 1. That's the weak interaction regime. Moreover, since we arrange this lambda case decreasingly, I can make such a statement. I found that the lambda case for k large enough are decaying exponentially, e to minus gamma k. Okay, and now I would like to show you the concrete results that I found for n equals 3. First, for weak interaction, we expect that the largest 3 occupation numbers are close to 1. So I consider 1 minus lambda 1 and so on. And indeed, I find that these differences behave as delta 6, delta to the 4, delta to the 4, which is a more number. And consequently, due to normalization, you find that all the other guys are also very close to 0. So lambda 4 behaves as delta to the 4, 4, 6, 8, 10, and so on. So there's a hierarchy. So going from lambda k to lambda k plus 1, we get 2 additional orders in delta. Which means if delta is a small number, these lambda k's have a clear hierarchy to each other. And this will also be important for us later. Actually, it's very funny. So I try to confirm this. Actually, these are more. First, I obtained these results numerically, and then I try to confirm them by perturbation theory. And it turns out that almost all textbooks are wrong that I found. At least these 10 or 15 that I checked. And there's only one lecture note, one of my former supervisor, Jörg Fröhlich, which presents this in the correct way. And I was really shocked about this. And it's more complicated than one would expect. Okay. And with high effort, I confirmed these numerical results up to 10th order in delta. Okay, so now we take these given results and do a pinning analysis. Okay, lambda vector is given. There's one problem. I told you we should restrict to finite dimensional situations. But our one particle Hilbert space is L2 of R. It's an infinite dimensional Hilbert space. So we should check lambda vector inside of this infinite setting here. Infinite polytope. Okay, polytope is not the appropriate word anymore here. But unfortunately, we know these polytopes only for very small dimensional settings. So we cannot check the position of lambda vector inside of the set. But there's one trick. It turns out that almost all natural occupation numbers are more or less 0. So the idea is to just forget about them. So let's just take the largest d natural occupation numbers and check the position inside of this truncated polytope. And mathematically, this is justified according to this statement. Assume that you find a distance of this vector to the boundary of this polytope. Then you can mathematically prove that the correct distance in the correct setting is the same modulo the largest neglected eigenvalue. This allows us to truncate the setting and do a truncated pinning analysis. Okay, let's do this pinning analysis. We start with the smallest non-trivial setting, so 3 electrons and 6 dimensions. For this setting, you already saw the polytope and the constraints. Now I wrote this inequality in a slightly different way. Lambda 5 plus lambda 6 minus lambda 4, no negative. The question is, if you plug in the complete physical result for this model, is this constructively saturated or approximatively saturated? So this is polytope. The complete physical result is given by this black curve here, just a qualitative picture here. For delta equals 0, for the zero interaction, we already know the starting point in this spectral picture. It's just the Hartree-Fock point here, the point which corresponds to 1, 1, 1, 0, 0, 0. And if we now switch on the interaction between the fermions, we will see that on a scale delta to the 4, the point will move along this edge here. On a finer scale, delta to the 6, the point will also leave this edge and will move more to the right, but it's still on the bottom area. And notice that the bottom area here corresponds to saturation of this constraint. So we just ask for the distance of this black curve to the bottom area. This is exactly the saturation here. And the concrete results are showing the distance behaves as delta to the eta, a very small quantity. But notice this is just a truncated setting. This setting has an error. The error is just lambda 7. So whenever we can neglect lambda 7, this setting is correct, and lambda 7 behaves as delta to the eta. So the truncation error is of the same order as the distance to the bottom area. So we found one first result here, a lower bound on the pinning order. So we already know that we are very close to the boundary, but it's not clear yet whether we're exactly on the boundary or whether we have a distance delta to the eta.
So how do you measure the distance?
It's just, so here in this finite setting is anyway irrelevant, but I just take the Euclidean distance. But you can also take the L1. Probably the L1 distance would be more appropriate because we just talk about the spectrum. So to improve our accuracy, let's take another eigenvalue, lambda 7, into account. Turns out there are four generalized Pauli constraints, and they're all saturated up to delta to the eta. This setting here is correct as long as we can neglect lambda 8, which behaves as delta to the 10. Here, since the truncation error is much smaller than the polytope distances, we finished our whole pinning analysis in this setting here. We found that we are not exactly on the boundary, but given that, we are surprisingly close to it, and we call this phenomenon quasi-pinning. Moreover, so here we just consider the weak interaction regime. I consider delta smaller. But it turns out that it's not only a weak interaction regime feature property. We also find out that if we plug in an interaction strength, which is comparable to the external potential, so equal 1, we find a distance which is more or less 0. It's 10 to minus 9. So you see it's incredibly small also for non-weak interactions. So I consider so far just n equals 3. So a master student of Matthias' group, so Daniel Ebler, he repeated the steps for n equals 4. And I did numerical brute force calculations for 5, 6, and 7. The results are again delta to the 8 quasi-pinning. So it doesn't depend on the particle number, n equals 3. It's actually also a poster which reviews these results here. Daniel. Moreover, I just focused so far on the ground state. So what about the excitations of that model? For n equals 3, I studied the excitations. I found that the first few, let's say 10 I think, were also quasi-pinned. But you can say the higher the excitation, the weaker the pinning. And after a while it vanishes for the 11th excitation. So we can say that quasi-pinning seems to be kind of ground state effect or effect of the lowest excitations. So far we found this very, very surprising physical effect. But it's not clear yet what it means for the n-particle picture. So it's just an academic question to check the position inside of the polytope. Okay, and now I would like to explain why pinning is interesting. Okay, what can we get out of it? For this, I have to introduce some notation, becoming slightly more complicated. Let's consider a generalized Pauli constraint, okay, such an inequality, with some affine coefficients, kappa naught, kappa 1, and so on. And let's say this given a lambda naught vector, which saturates this constraint here. So we have exact pinning. Delta of lambda naught should be 0. The natural question is then, what are the implications for the corresponding n-particle fermion state? Can we say something on psi? This is actually exactly the question of physical relevance of pinning. Can we go from the primitive one-particle picture back to the n-fermion picture? So naively, I would not expect but this is possible. But fortunately, it turns out it's possible. As a kind of warm-up, let's consider a spectrum which is given by 111,000. Whenever such a spectrum is given, you can directly tell me that by choosing an appropriate one-particle basis, you can write the corresponding psi n as one single slated determinant. And the good point is that this statement is also stable under small deviations. If the spectrum is approximatively this Hartree-Fock spectrum, then you can write psi n approximatively as the slated determinant here. So now let's generalize this to the generalized Pauli constraints. So for this given lambda naught, there's a corresponding psi n. Probably don't know it. The experimentalist doesn't know it, but it's fixed. Okay, God knows it. Somebody else might know it. And let's denote it by psi n. So for psi n, in principle, one can calculate rho 1. It's well defined. And we can diagonalize it. We get, again, the natural occupation numbers and the natural orbitals, the eigenvectors I here. These natural orbitals, they of course, define a one-particle basis, the one-particle Hilbert space, so B1. And we can use this one-particle basis to define a basis for the Fermionic Hilbert space. We just take the slated determinants. So just take n of those one-particle states, take the tensor product, and anti-symmetrize it. I collect all those integers as a list, I bar, and this is then my symbol for a slated determinant. This one defines, of course, a basis for the Fermionic Hilbert space. In respect to that basis, we can expand our psi n. Okay, psi n is just expansion over these I bars, Ci, expansion coefficients, and slated determinants. Okay, let's come back to our constraints. So this was the constraint that we considered. And for this given constraint, which is saturated by lambda naught, I would like to define an operator. I'd like to define this operator here. I just copy more or less this constraint here, but I replace these numbers lambda 1 up to lambda d by operators. So these are the creation annihilation operators with respect to these one-particle states, to these natural orbitals. And here I add identity. Formally, this operator d hat depends on psi n, okay? But this is not a problem here. Then the mathematical statement, this is important message here. Mathematical statement means whenever lambda naught is pinned to this facet, the corresponding d hat operator applied to psi n is equal to 0. This is the statement. And then you can, of course, plug in the corresponding expansion for psi n here and use the linearity. So sum over all I bars, C I bar, d hat I bar is equal to 0. And here, notice that these I bars are exactly the eigenvectors of d hat. Okay, this mathematical statement immediately implies a selection rule. Assume, okay, you can easily calculate this, apply d hat to one single slated determinant for some list here. Now you can directly see whether it's 0 or not. And whenever it's not 0, you can directly see that this mathematical statement here implies that the corresponding coefficient has to vanish. So we learned that exact pinning leads to a selection rule of slated determinants. Whenever you have exact pinning, quite many slated determinants have to vanish. So pinning corresponds to simplified structures of the corresponding Fermionic quantum state. And at least for smaller settings with 3 fermions and 6 dimensions, I can also prove that this statement is stable under small deviations. If you have quasi-pinning, you have approximately this structure. This I can give you first an example that Mary Blasuski already mentioned at the beginning. So consider 3 fermions and 6 dimensions. So you saw the polytope of that. This Hilbert space has dimension 20. So 3 fermions for 6 modes, that's 20. And assume now that our physical state is pinning this generalized Pauli constraints. What does this imply for the structure of the corresponding 3 fermion state? Well, you can show that psi 3 can be written as just a linear combination of 3 slated determinants with some coefficients alpha, beta, gamma, and some natural orbitals 1, 2, up to 6. So you see we go down from 20 to 3. So pinning leads to a simplified structure. So pinning is physically relevant, fortunately. So we can make a conclusion from the one-particle picture back to the important n-particle picture. So one first application of that, just an idea, is an improvement of Hartree-Fock. So let's say there's given a Hamiltonian, let's say for 3 fermions, and it's so difficult to find the ground state analytically. So we would like to approximated, for example, variationally. So there's a Hartree-Fock method, which works quite well for atoms. So the idea for Hartree-Fock is make this ansatz here, take 3 one-particle states, 1, 2, 3, with a slate determinant, and minimize the energy functional with respect to these states. So in this polytope picture, it means consider all points which are corresponding to this Hartree-Fock point, and then optimize your 3 states in your d-dimensional one-particle Hilbert space and look for the energetic minimum. And the result is in the Hartree-Fock ground state. And whenever the concrete unknown ground state is close to the Hartree-Fock point, this approximation was very good. But if we are more far away, let's say here, Hartree-Fock is a bad approximation. And our suggestion is to replace the Hartree-Fock ansatz by this pinning ansatz. Consider all points which are corresponding to this facet, to this bottom area. So this pinning ansatz here. And this will not only improve Hartree-Fock, which is trivial because it's a more generalized state, but the statement is we improve Hartree-Fock by several orders in the interaction strength. And of course, such ansatzes already exist in quantum chemistry. So this multi-configuration self-consistent field, you just linearly combine, let's say, 10,000 slate determinants. But our message is that since we choose these slate determinants very carefully, we can increase the one-particle Hilbert space. So if you plug in something to the computer, you always have to restrict your one-particle Hilbert space. And our advantage is that we can choose a very, very large one-particle Hilbert space because we just need 3 slate determinants instead of, let's say, 10,000. This is just an idea. So I would like to conclude. So we learned that the anti-symmetry, if you translate it to the one-particle picture, leads to the so-called generalized Pauli constraints, which were found by Alexander Klyatchko. Then, by studying a concrete physical model with interaction strength delta, we found that the distance to the Hartree-Fock point behaves as delta to the 4. So the Pauli exclusion principle is pinned up to corrections of delta to the 4. Nevertheless, the distance to the boundary of the polytope is much, much smaller. So it behaves as delta to the 8. We call this in effect quasi-pinning. Fortunately, this quasi-pinning is physically relevant in the sense that it leads to structural implications. We can suggest a Hartree-Fock improvement, and slightly provocatively, we can ask whether fermionic ground states, whenever we trap a few fermions in a harmonic potential, for example, we might expect that we always get this quasi-pinning, and then we can say, well, probably fermionic ground states are simpler than appreciated. The structure is simple. Okay, and I would like to finish my talk with an outlook of further results that I found. I studied one-dimensional models in a discretized way, switch on a harmonic trap, and then some interaction, for example, harmonic or Coulomb or whatever. And I found that quasi-pinning is generic, at least in this discretized setting for one-dimensional models, for all interaction forms. This goes a little bit in the direction of Laughlin's result, that the interaction form throughout the fermions doesn't really matter for some physical situations. Also studied the Hubbard model with just a few lattice-sites, 3 lattice-sites, 4 lattice-sites, and a few electrons hopping on that. It's not the macroscopic regime. And it turned out that you find exact pinning for 3 lattice-sites and 4 lattice-sites, but this pinning vanishes for 5 and 6. So it seems that the Hubbard model is borrowing from this pinning viewpoint. But the new insight is that exact pinning can only appear if the model is very, very primitive, if the model is full of symmetries. Of course, if you have 3 lattice-sites with translational symmetry and spin as good quantum number, the model is so simple that some slate determinants are exactly 0. And we have application quantum chemistry, like to make a statement on ground states of atoms with James Whitfield and Matthias and so on, with David. It's not so easy to get some numerical results for atoms, so it's in progress. I would like to get an understanding for this quasi-pinning. I still don't yet understand the mechanism behind it, so it's more difficult than expected. Also collaboration, where we check quantum Hall states. So far we just consider weakly interacting systems. We are already very close to the Hartree-Fock point, so Hartree-Fock is already a good approximation, and just beating it a little bit is not that spectacular. So it's nice to check highly correlated quantum systems. Naively, I don't expect that the polytope should play a role for strong correlated systems, but we will see. And my intuition why this generalized Pauli constraint might be relevant for physics is this here. So the anti-symmetry of the n-Fermi wave function, which leads to this generalized Pauli constraint, is in strong conflict to the energy minimization for the ground state. So in the sense that if you skip the anti-symmetry, you would find much lower energy ground state. So the bosonic ground state to be much, much lower than the fermionic one. So somehow I would expect that the generalized Pauli constraint should play some role. Okay. But thank you very much.
So we have some minutes for questions and comments.
How do you do the calculations to obtain the inequalities?
Oh, this is very complicated.
Any intuition towards it?
Yes, that's actually. It is a variation principle. It's a generalization of the Chi-Fan variation principle.
Oh, sorry.
Do you know the Chi-Fan variation? Just take a Hermitian matrix. And let's say you would like to get the largest eigenvalue of this matrix. Say a Hermitian matrix. And with them the eigenvalue of lambda, which are arranged, let's say, decreasingly. You would like to express lambda 1 in a fancy way. So what you first consider, take rho, your matrix, then an orthogonal projection operator on a one-dimensional subspace V, take the trace of that, and then maximize this over all one-dimensional subspaces V. Okay, there's actually a generalization of this. You can do actually the same for minimum, or if you just take, you can also do it for the largest k occupation numbers, the smallest k. There's actually a generalization of this. You can just take some arbitrary sums, lambda 1, lambda 7, lambda 9, and so on. Then you copy more or less the same as here. I mean, it's just a very primitive idea. Probably you won't understand the details. And here you optimize over all over some three-dimensional subspaces, not over all. And the corresponding object is so-called Schubert cell or Schubert variety, which depends actually on this 1 to 179, and also on the density operator rho. Of course, not very spectacular that such a variation principle exists because it depends. This area depends on the rho. The nice point is, if you choose exactly the Schubert cell or Schubert variety here, it's a very specific set here, then it has very beautiful mathematical properties. Okay.
And the Schubert cell is coming from the anti-symmetrization?
Oh, it's not yet about anti-symmetrization. So this is the first step. It's not yet related to these constraints, okay? But then in the next step, you would like to use this, okay? I can tell you for what you would like to use it. I can show you. I cannot tell you how to derive this generalized Pauli constraint, but I can tell you how to derive some marginal constraints. Okay, and then one marginal problem is this here. You can consider if this multipolarized quantum system consisting of A and B, and the total system is AB. And I would like to ask which tuple of spectra lambda A and lambda AB vector are compatible to each other in the sense that you can find a total state rho AB which has these eigenvalues, and which leads to a marginal rho A which has those eigenvalues. Okay. Well, what you then do, you just derive necessary constraints on the compatibility of those guys. Okay. You just assume there's given a rho AB such that tracing out B, okay, will lead to rho A. What you then do is you use this variation principle. You start with the sum of eigenvalues of this guy minus some eigenvalues of this guy. So this is some on the left-handed side. There's some lambda IA. You sum over some specific i's. It's just a structure to give you an impression. It's a very, very rough structure. Then you plug in both variation principles here and there, and you see this about this. One of the variation principles just refers to rho A, and the other one refers to rho AB. But you can lift the first variation principle by plugging in, instead of row AB, and adding the partial trace over B. And then you optimize over two sets at the end. You have just two variation principles.
So, Christian, can you make your answer simpler? Because it's too technical. I think we have more maybe.
Or
more
I just need 20 seconds to finish.
Okay.
At the end, you have somehow two variation principles, and here you optimize over such a set, and here over another set. And then you assume that both sets have one common element, that you can plug in this common element, gets a smaller equal, and it turns out that the arguments of this minimization are identical. Then you have 0. So at the end, what you have to do is you have to start at the intersection of these Schubert varieties. And whenever you find a common element in two Schubert varieties, you can write down one inequality. And one would like to do it systematically, and this is where this cohomology theory of like varieties enters. This also Klyashko did very beautifully.
Thank you.
It's just this variation principle of basic state.
Yeah. Please.
Yes, so I guess you could also try to, instead of doing the calculation, just look at experimental data for the one-particle reduced density matrices. And this isn't typically hard, but what is much simpler is to look at diagonal elements of your reduced density matrix. So what kind of, so because you have condition on the eigenvalues, this automatically gives also conditions on the diagonal elements, okay, because of this majorization kind of things. Does it give non-trivial inequalities on how the diagonal elements of your reduced density matrix look like? Because that would be very interesting, because there's lots of experimental data for matrix.
So the point is, if you don't know the eigenvectors of your density operator, if you have no relation between the two basis sets, so the basis that you measure in the experiment and the eigenbasis of the operator, if there's no relation that you know, then there's only Pauli's exclusion principle on these diagonal elements.
So there's nothing that survives.
No, unfortunately not.
Nothing.
No, actually, I mean, actually, Harold Kuhn was one of the people who solved the Pauli problem. So there are necessary and sufficient conditions, which were done by Joost Lippin Kuhn back about 1969 when I did my thesis, on the diagonal elements in a product basis, such that there exist off-diagonal elements that will give you, but that's not enough. That's just a combinatorial problem. Because now, one thing that's a little misleading here is when you do these variational, to reduce, for the one-body reduced density matrix, you can state necessary and sufficient conditions solely in terms of the eigenvalues. For the two-body density matrix, this is not true. I will discuss this tomorrow because it's a very challenging question that I've asked several times, and somebody told me they were going to send me an answer. To find the local invariance that will allow you to even state the conditions for the two-body problem.
But so the statement is, I give you any diagonal element.
They have no restriction.
On the equation, there's always a pure state that will give rise to these elements.
Yeah.
Yeah.
Maybe we have time for another question. Yeah.
That's the one.
Okay, so yeah. Maybe yeah.
Well, so do you have any physical intuition why we should expect the spectrum to form a polytope?
Sorry, I didn't understand you. So why we have quasi-pinning?
No, why we should expect the possible set of spectrum to form a polytope? Is there any physical reason for that? You have any physical intuition for that? Or maybe put it differently, the fact that there's a polytope, does it help us to learn something about physics in this case, apart from the states being antisymmetric?
So I would say the fact that there's a polytope does not imply that much for physics a priori. So I think in general it's very hard to get some physical use of the quantum margin problem. I think the polytope plays only a role if it limits the physics somehow.
It becomes is the polytope becoming kind of a curved thing when n goes to infinity? Not n, but the dimension of the basis dimension.
There's always a polytope. I mean,
Yeah, but does it?
The polytope is only for the one-body reduced density matrix. You don't, I mean, I don't believe
Any
you get a
physical
polytope with
intuition
two
for
bodies.
that? Why it should be a polytope?
I would say it's just a mathematical question. I have no physical idea, but also no mathematical.
Physical intuition.
No mathematical, also no.
Okay. What's known is that the solution to the unrepresentability problem cannot be a function of what you choose for your one-body basis set. So it has to be expressible in terms of local invariance. And for the one-body reduced density matrix, the local invariants are the eigenvalues.
Oh, I see.
And so therefore, the solution is expressible in terms of inequalities for the eigenvalues, which leads to these polytopes.
But why it
This
should
does
be
not
linear?
generalize to the two-body density matrix.
Why it should be linear? Because you have eigenvalue, it's linear, but why it should be the
I think all our
summation of
experts
them,
have
yeah.
left right now for this talk, but the experts are Michel Vernier and Nicolas Resser.
I'm obviously not an expert.
So it's Kirwan's convexity theory that gives you convexity proofs.
But you get infinitely many inequalities, I guess, no? If the dimension grows.
Yeah.
What
Yeah,
if
so
more
now we're
numbers?
discussing two processes at the same time, but just convexity, I don't know of any simple proof for convexity apart from like going through Kirwan's theorem.
I see.
Well, there's
Or
a
maybe
simple
there
proof.
are-
Sorry, I mean,
We
it's
can-
a
I
very
can tell whoever wants
but
to after.
maybe it's
Okay.
tea time. We can continue talk if you continue to discuss if you want. So let's take a question again. I mean,